All right, ladies and gentlemen, today we're going to take a look at section 10.6, the volume of prisms and cylinders. So you're going to notice there's a lot of common themes as we move along here. So hopefully what you saw in 10.4, 10.5 with surface area, you'll get the flavor and the feel of that for volume, which to me is actually an easier concept to work with than surface area. So hopefully these videos will be helpful for you and your guidance on this topic. So two targets that we're going to look at: learn and apply the formula for the volume of a prism, and the second target is I can learn and apply the the formula for volume of a cylinder. So the volume of a three-dimensional figure is the number of non-overlapping unit cubes that a given given size that will fill the interior exactly. So it's truly the 3D concept, and it's inside the three-dimensional figure. Okay, so what you have is dealing with this concept of if you were filling up your, for example, Starbucks cylinder, which isn't really a cylinder, they mess with you, that's a different shape that you'll have to deal with a little bit later in your mathematical career. But if you're filling that up with the liquid, not like covering the actual cup itself, which is much more of a surface area concept. Cavalier's principle says that if two three-dimensional figures have the same height and the same cross-sectional area at every level, then they have the same volume, even if one is right and the other is oblique in nature. Okay, remember, if it's oblique, that the height is going to still have to be formed just like it would at the doctor's office outside of the triangle, or in terms of this, the prism, which is totally okay. Notice that's illustrated down below here. So for the formula for volume of a prism, what you're going to be dealing with is the area of the base times the height. Notice the area of the base is indicated with a big B. This is a big B, not a little b. The big B is the area of the base. That's important. It's a concept that you have to calculate. That's why that letter is capitalized in the formula. Okay? There's a couple special circumstances, though, that we have some easier formulas that you probably recognize from previous math classes. So for a rectangular prism, like a tissue box, you have your length, your width, and your height that you just multiply together to get the volume. And if it's a cube, since all the sides in a cube are of equal length, you just cube that value to get the volume. Once again, volume is three-dimensional, so units will be like meters cubed, inches cubed, feet cubed, centimeters cubed, etc. Okay? So, for example 1, find the volume of the prism round to the nearest tenth if necessary. So in this case, you can use the general formula, which I typically roll with, or if you recognize it, oh, this is a rectangular prism, a right one, not a wrong one, didn't here all day. But incidentally, you could use that formula as well. So basically, to get the volume, you would just have, in this case, the length, the width, and the height. And if you chose to go with area of the base, you could. But once again, as we've discussed in class, the order in which you plug these in really doesn't make a huge difference. Although I think most people would interpret the length here as 3, then the 13, the corresponding width is 3, and then the height would be 5, which technically is the distance between the two bases. Plug that bad boy on a calculator, bada bing, bada boom, you should get 195. Once again, the unit, though, is centimeters, but cubed. Not bad, right? Not bad. So you got your swagger on, you're feeling pretty good about life, liberty, the pursuit of happiness, and then you see example 2. And you think, Funfar, there's not enough information to do this problem. And I think, yes, there is. Because you have a regular hexagonal or hexagonal prism, and it happens to also be right. So we know that it's standing upright. We know that its lateral faces are in the shape of rectangles, which is an important bit of information. Okay? So what that means for us is this. We can't use either of these two formulas. We can't use length by width by height because it's not a rectangular prism, and it's not a cube, so we can't use s cubed. So we have to use the general formula, which is area of the base times the height. Oh, this is where things get interesting, though, as I think some of you have already seen. The base is a hexagonal, and it's regular. So, oh no, that means we need to take and work with our good friend 1/2 little a P. Uh-oh, what does that even stand for? I don't even know. Take a breath. Think about it for a minute. Remember, this is the apothem. The apothem, which is the distance from the center of the hexagon to the edge, making a right angle. And then, oh yes, remember, it makes some triangles. We'll draw that off on the side to help you here in just a minute, okay? But that apothem is definitely going to be a little bit tricky, all right? And then the P is the perimeter of the base, which in this case, it's the perimeter of the hexagon. Remember, it's key that this hexagon is indeed regular. Otherwise, we would not be able to utilize that formula. So, a couple quick things off to the side. If I was to expand on that triangle and I drew it larger, not terrible, boom, apothem's here. I don't know the length of it, okay? But I do know the length of the side because if this is 9 here, this is also 9 up here. So the whole bottom piece is 9, which then implies that this piece right in here is 4.5 because it's going to be half of that, 4.5 feet, okay? You're like, I still don't have enough information, fun for. I mean, I got a right triangle, but I need an angle measure to do anything more. Don't forget from our studies in the previous chapter that the angle up here is going to be 360 because that's the number of degrees around the center of these regular polygons, but then in a hexagon, there's 6. So it's 360 divided by 6, so 60 degrees. That's the whole angle. But if you look here, how big is this? It's not 60. It's 30 degrees. It's cut in half. So you do have a 30, 60, 90 situation. So you can either use some trig or you could use special right triangles. It's totally your call. It's up to you. I mean, I really don't care. You do you. And you could use the 30 degree or you could use the 60 degree. It does not matter. So there's really 3 different ways that you could approach this, okay? I will do the trig. I'll tell you that I know the apothem is 4.5 square roots of 3. I know that because I know my special right triangles. But I don't know, maybe you don't know. I don't know, maybe you don't know. So we're just going to do a little trig. So I'll go with, it'd be tangent. And I'll go with a 30 degree because most of you, at least in my class, seem to work with the 30 degree well. Then you have the opposite side, which is 4.5, over the adjacent side, which is little a. I always put that over 1, cross multiply, and solve. So when you do that, you'll end up having the tangent of 30 degrees times a, and that's going to equal 4.5. So you would then have to divide both sides by the tangent of 30. Sorry, that's a little squeeze there in the bottom. Little squeeze. So really, you'll have 1/2 the apothem, which you can either do in special right triangle form or using some trig. So if I use my trig, it's tan of 30 degrees. Oh, just plain. That goes on the bottom. Got to be careful here, people, because even I make mistakes. I'm certainly flawed, right? Everyone that has me knows that. So you have that 4.5 divided by the tan of 30, okay? Another way would have been having tan of 60 divided by 4.5, okay? So that is for the apothem. The perimeter portion, we would be looking at, well, you have 9, 9, 9, 9, 9, 9, and I'm not saying no in German. But rather, I'm counting that there are 6 9s. So the perimeter here is just going to be 6 times 9, which would be 54. And that would just be 54 feet. But I'm not going to include my unit because I don't want to get too messy here. The final piece, that height, is the distance between the bases. It is not the height of the triangle. It's not like the apothem. It's the height between the 2 hexagonal bases. So that's 12. So that'll be times 12, okay? Put this bad boy or girl on your calculator. Beep, beep, boop, beep, beep. I'll give you a moment, okay? 1/2, 4.5 divided by the tangent of 30 degrees times 54 times 12, and you should get something in the neighborhood of 2,525.3. Unit, feet, cubed. Now, if you need to, please go back and rewatch that. Some of you were very, very proficient and, in fact, advanced with this skill in the last chapter. But others might need to pause and look at this again and really think about it, okay? The only thing new is adding in the volume, the three-dimensional component. Okay, so I'm going to have you try example 3 here in a moment and then come on back for another video. Stay tuned, everyone. Bye.